The Schubin Talks, Next Generation Imaging, Higher Dynamic Range, is presented by SVG, the Sports Video Group, advancing the creation, production, and distribution of sports content at sportsvideo.org.
Welcome to the Schubin video series on Next Generation Imaging. In this video, I'm going to talk about Higher Dynamic Range, or HDR. So the first question is, what is dynamic range when we're talking about imaging? Well, it's the range from the darkest to the lightest perceptible parts of the picture, or lightest to darkest, whichever way you want to look at it. Essentially contrast ratio, and HDR means higher dynamic range. Now, the dynamic range depends on both the desired screen light, like how much brightness you can put onto the screen, and the undesired reflections. So in a cinema, we have very low desired light, but also extremely low undesired light. It's a very dark room, and on the right I'm showing that the standard for brightness in cinema is 48 nits. A nit is a candela per meter squared, and for 3D it tends to be about a quarter of that, but people are still working on 3D issues. In the home, we have medium desired light. The TV sets tend to be much brighter than movie screens, but we also have medium undesired light because people leave lights on while they watch TV. And again, on the right, I just did a quick survey of TVs in 2015, and the desired light, the brightness for white, seems to range from about 138 nits to 1,000 nits. But the reflected light also has quite a range. The reflections range from 0.7% to 2.6% of light being reflected off the screen. And then, just to mention it, handheld devices also have medium desired light output. It's comparable to a TV set, but very high undesired light because they tend to be used outdoors where there's sunlight, and sunlight is quite bright. Now, I need to mention that bit depth is not the same as dynamic range. In theory, high dynamic range needs no more bits than standard dynamic range. The bit depth should simply determine the signal-to-noise ratio, or how much grain you're seeing in the picture, if you will, as long as at least 1/2 of the least significant bit is noise. Now, this is something that the audio engineering community has worked out very nicely, but the video community has not worked out so nicely. So as a practical matter, if you don't seem to have enough bits, you do have contouring in the picture, which I'm showing on the right here. It's those undesired lines that you're seeing. You might see them sometimes in a sky or something like that. It's very noticeable. It's halved for each additional bit, and it's eliminated when, again, the least significant bit, 1/2 of it, matches or is less than the amount of noise. So, why do we want high dynamic range? Here is an image taken at a ski lift, obviously not during the winter, and you can see the trees outside, and maybe they're a little bit overexposed, but you can't really see anything inside. So now we go to a brighter exposure, and now the trees are definitely overexposed, and we can see some of what's happening inside, but we still can't really see what's going on inside the gondola, and we don't really know quite what's going on in the foreground. And so we open up the exposure some more, and now we've properly exposed for the face inside the gondola. We can see that very well. We can see the things in the foreground very well, but the outdoors is just a total blur of whiteness where formerly we had some trees. Now, there's lots of good news associated with high dynamic range, and there's really no bad news from a technology standpoint, but there's a lot of trickiness that we have to deal with. So let's look at the good news first. This is from a presentation at the Technology Summit on Cinema at the NAB convention in 2014, and it was done by the Swiss Polytechnic Institute in Lausanne. And other people have come to pretty much the same conclusions. Now, the green material is what I've added here. So for today's reference monitors, we have essentially a poor response by viewers. And as the brightness increases and therefore the dynamic range increases, because we can't get rid of darkness, it can only be as dark as we start, the perception of picture improvement increases tremendously. So good news number one is you actually get the most bang for the data out of higher dynamic range. Now, what do I mean by that? Well, here are 3 charts of viewer preferences, and the one on the right is the one I've just showed you, and I've normalized the vertical axes, and the distance from the top is how much improvement there is. So on the left you can see going to a higher spatial resolution, going beyond HDTV, and there's an improvement, but there's a small improvement, and to get even a half grade of improvement, you need 8 times the data rate, so you need maybe 16 times the data rate per grade of improvement. And in the middle I'm showing higher frame rate, and a doubling of the frame rate gives you a grade of improvement, so that's 2 times the data rate for a grade of improvement. And at the right I'm showing the high dynamic range, and theoretically again you don't need any increase in data rate. Now maybe you'll need 20% either to eliminate that contouring that I mentioned before, or for transmitting the higher dynamic range separately to higher dynamic range TV sets while you're also simultaneously transmitting to standard dynamic range TV sets. Now that's one set of good news. Here's good news number 2. You can get more colors without changing the primaries in the TV set. So on the left is one of those color diagrams that you might be familiar with, but the white line in it is not what you're typically familiar with. That's the range of surface colors. It's from a paper that was delivered in 1980 by Michael Pointer. And on the right is something else from that paper, and at the top is a higher brightness, in the middle is a medium brightness, and at the bottom is a low brightness. And you can see that the shape of those visible colors changes with the different brightnesses. So if you can offer more brightness, then you can offer more colors without changing the color primaries of the display at all. You can get a saturated bright yellow, for example. Good news number 3, you may not need to do any shading when you're shooting. Here is something that was shown by Peter Senton of Grass Valley at the HPA Tech Retreat in 2015, and this is taken inside the production area at MotoGP Valencia, and they were doing a high dynamic range test, and you can see that the shader or painter, the video operator, grader, whatever you want to call it, who's doing standard dynamic range, has his hands on the controls because he's constantly dealing with changing lighting conditions, but the shaders for high dynamic range on the left are just kind of sitting there looking at the pictures, no hands on the controls because the camera can handle the full range of lighting conditions. Here's good news number 4. There's really no new technology that's needed. This is a presentation at the NAB convention in 2015 by JVC, and you can't really tell the high dynamic range from this image. You need a high dynamic range display, and I needed to shoot it with a high dynamic range camera. But you can see that they're doing a presentation, and people gathered around this. They were very excited by the good-looking pictures. Here is another shot from the HPA Tech Retreat in 2015, and this is with a Christie laser projector. It's very high output, it has no speckle, it can offer high dynamic range, and almost as many colors as anybody has asked for. So this is available both for home and for cinema. The technology is here. Getting it to the technology is a little tricky, as we'll see in a moment. And from a camera standpoint, here is an amazing picture. What's amazing about it is the only light that you're getting in this scene is coming from the lamp that you see at the bottom right, which is aimed into the lens of the camera. And this was actually shown at the NAB convention in 2008. It's a Grass Valley Sensium sensor. It's a CMOS sensor, and CMOS sensors allow you to control the exposure on each photo site individually. So there's a 10 million to 1 contrast ratio in this picture. You can see the individual coils of the filament of the light, as I'm showing at the bottom right, as well as everything else in the room, all of the chips on the chip chart and so on. There's more than 23 stops of dynamic range in this image. Well, tricky issue number one, how do we get the high dynamic range to the TV? Some people are watching broadcasts, some are getting cable, some are getting satellite, some are watching things directly from the internet. There's also cinemas. How do we code this? It's certainly possible to come up with. Many people have come up with different coding mechanisms, but they haven't all agreed on it at the moment, and so we're still waiting for that standard for how we should transmit this, or an agreed standard in any case. Tricky issue number two, which TV do we prepare for? So this is an image that comes from a Dolby brochure showing their high dynamic range testing, and there's some nice high dynamic range material, but do you prepare the material for the high dynamic range TV? Do you prepare it for a standard dynamic range TV? How do you know how many lights are on in the house? Remember, there's a big range of brightnesses that the TVs can put out, and it's more controlled in a cinema, but it's still an issue that we have to deal with. Now, here's something that I prepared. It's a very, very broad range of shades of gray with these words on it, and there's a white section of the screen on the left and a black section of the screen on the right. And I don't know what your computer is going to show, but you're probably going to see some words on the left side and probably not see any words on the right side. Now, I can adjust that pretty easily by reducing the contrast ratio, and now you can see more of those words that I prepared, but this doesn't look the way that I wanted it to look. There's no white on the left, there's no black on the right anymore, it's just different shades of gray. So preparing high dynamic range material for standard dynamic range is not a trivial matter. It's not something that can't be done, but it's not trivial. Then we have tricky issue number three, prepare for which scene. Here's that same image that I showed you before, and I told you that Grass Valley said that the high dynamic range shaders didn't have to do anything, but this picture probably doesn't look the way that you would want it to look. You'd rather have more detail in the dark parts, so it could use some more preparation. Here's tricky issue number four. How do we deal with power consumption in the home? Now, at the right, I'm showing a test rig that was used for some perceptual experiments. They actually had people looking directly into the lens of a digital cinema projector, but with a ground glass screen in between, so that they could see extremely high dynamic range. But here's some actual information on a particular television set. This is a Samsung television set, and it says that in typical operation it's going to consume 110 watts, and in peak operation it's going to consume 351 watts. Now, Dolby, for its demonstrations of high dynamic range, came up with a special monitor called a Pulsar Monitor. It has 4,000 nits of output, which is much more than any home TV at the moment. But to do that, the monitor actually had to be liquid cooled. So some people say, well, the high dynamic range is just going to be used for what they call speculars, like the glint off chrome or off a piece of glass or something like that. But what happens if someone decides to shoot a snow scene and make the snow as bright as we might see it? That might actually violate the law in places like California, where there's only a certain amount of energy that a TV set is allowed to use. Then we have tricky issue number 5, the interaction between high frame rates and high dynamic range. I've shown this in the other videos. High dynamic range makes motion defects more visible. And then tricky issue number 6, which is interaction between high dynamic range and high resolution. If you take an imager for, say, a 2/3 inch camera that's high definition, it has a photo site that's 5 microns by 5 microns. If you take the same size imager, as some manufacturers are doing, and turn it into a 4K resolution, then each photo site has only a quarter of the size and therefore can capture only a quarter of the photons. Now, this is something that can be dealt with some processing, but it's not something that's commonly dealt with yet, so it's yet another tricky issue. So the conclusion is work remains to be done. The other videos in this series cover high spatial resolution, higher frame rate, and an introduction to next generation imaging. Thanks for watching, and please enjoy the other videos.